My name is Reuben Covey, and I'll be discussing my results from Lab 2 surrounding the topic of the motion of a falling object. In this lab, we tracked the motion of a falling system, a dry eraser, and then created two computational models, one with the force of drag and one without, to compare our results with. The purpose of the lab was to study the force of drag, gravity, as well as the effects of a non-constant force. After comparing the results, we found that the model that included drag almost perfectly aligned with our observed findings. The important physics principles were the force of gravity, which is equal to negative mg, the force of drag, which we took to be equal to the speed squared times a constant b, which we chose to be equal to 0.02, as well as the velocity update formula. Additionally, we used two different versions of the position update formula, one of which calculated the arithmetic average for velocity using vi plus vf divided by 2, where the force was constant, and one of which used vf as an approximation for v average when the force was non-constant. The first step was to complete the real-world experiment where we extracted position and time data using the tracker software. Our observed data, as well as a graph of position versus time, can be seen here. It's important to note that the initial time is set to 1.74 seconds because this is the point in our video, which is in the top right corner, where our system began in free fall. We also recorded the mass of the system, the dry eraser, which will come into play for the computational model. The next step was to create our computational models. For our initial conditions, we set mass to be 0.0091 kilograms, initial velocity to be the zero vector, the initial position to be 0, negative 0.70, and the initial time to be 1.74. These are all the values that match the initial conditions of the data from our real-world experiment and thus are set to be the same for maximum accuracy. For the model with no drag force, we calculate Fg to be negative g times mass, which, since this is the only force, is also our Fnet. We then update the velocity using the velocity update formula, and then update the position using the position update formula for a constant force. Finally, the time is incremented to move forward in the loop. The resulting position data can be seen in the graph here on the right. For the next model that included drag force, we for the most part did the same exact steps as before while adding the force of drag. To do so, we first chose the proportionality constant b and set it to be 0.02. From here, we calculated the force of drag by squaring the system speed and multiplying it by both b as well as the directional vector j hat, which points in the opposite direction of the system's motion. We ended up choosing b to be 0.02 because this was the value that gave us the most accurate results when compared to our experimental data. Because we now have two forces, we calculate Fnet to be the sum of both Fg and Fd, and the resulting steps are now the same as in the model without drag, except we will be using Vf to be V average when using the position update formula because we now have a non-constant force. The resulting position data can be seen from this model on the right. As we can see from the table and graph below, the computational model without drag ended up having the system accelerate too quickly, causing its displacement to be much greater than its observed displacement. The model with drag included, however, almost perfectly predicted the motion of our falling eraser. The biggest source of error was the lack of drag force, which when not present, there is nothing to counteract the force of gravity, and the system becomes predicted to accelerate much too quickly than it does in reality. Even with the addition of our estimate of the drag force, this is still a possible source of error because we are using a simplified version of the drag force calculation, which does not take into account the shape and/or other properties of the object that's in free fall. For the extra what does it mean question, the velocity versus time graph from the model with drag, shown on the top, shows terminal velocity, while the graph in the middle from the model without drag does not show terminal velocity. In the case of terminal velocity, the net force becomes zero, thus causing no further acceleration and a constant velocity from that point on. For the what-if question, we can see that the model at the bottom, where the system was initially thrown, thus giving an initial velocity of negative 1 meters per second, still results in the exact same terminal velocity as before at around negative 2.1 meters per second. Thank you very much, and I hope you enjoyed.